So good morning. So I am Professor Krishnan from the Department of Aerospace, and I am the convener for the Axis Bank Center for Math and Computing. We are very excited to have one of the very distinguished speakers, Professor Reddy. So I take great pleasure in having this lecture. This lecture is arranged in association with Axis Bank and SPARC. SPARC stands for Scholars Pursuing Advanced Research in Computational Mechanics. It's a Government of India program. And I think this is also live streamed. Am I right? No. It is not? Oh, they don't. Okay. We will have this one videograph and put it on our Axis Bank website. So I take great pleasure in welcoming Mr. Reddy. I request Satish to give him a bouquet. So I also take great pleasure in welcoming some of the SPARC members here. Mr. Satish Nagarajaya from Rice University is here. Professor Anand Ramswamy, Chair of the Civil Engineering Department. And I also welcome Mr. Manohar. So before we start, it's my customary to introduce Professor Reddy. I know most of you know him, but it is not proper if I don't tell him a few words about his contributions. So I take pleasure in introducing him. So Professor Reddy is a very distinguished Regents Professor and the holder of O'Donnell Foundation Chair in Mechanical Engineering at Texas A&M University, College Station. Dr. Reddy is an ISI highly cited researcher. He is known for his significant contribution to the field of applied mechanics through the authorship of large number of textbooks. Imagine how many he has, 25, and about over 800 journal papers. His pioneering works in the development of shear deformation theories that bear his name in the literature as Reddy's third order theory and Reddy's layer-wise theory have had a major impact and led to new research developments and applications. Some of the areas on shear deformation theories and penalty finite element models of fluid flows have been implemented into commercial codes such as Abacus, NISA, and Hyper-Extrude. In recent years, Reddy's research has focused on the development of locking free and shell finite elements and non-local and non-classical continuum mechanics problem dealing with architected materials and structures and damage and failures in solids. Dr. has received enormous amount of honor. Imagine his CV is over 250 pages. So one whole session can be had, and I will just cite some of the recent ones. He has got the Lenovo Da Vinci Award from the European Academy of Sciences, 2023 Michael Paidos's Medal from the Royal Society of Canada, 2022 IACM Congress Medal. He has Timoshenko Medal, Theodore von Karman Medal, and many more. He is also a member of the 8th National Academy, including Indian Academy of Engineering and US Academy of Engineering, and a foreign fellow of the Canadian Academy of Engineering, Brazilian National Academy of Engineering, Chinese Academy of Engineering. The list goes on. So I'll stop here because we want to hear his technical lecture. We all know how distinguished he is. And today he's going to talk about a very important problem. How do you manage between finite element methods and finite volume methods for those who are working in solids and fluids? And this topic is very much relevant to the center that I am running, that is Axis Bank Center for Math and Computing. And I welcome Professor Reddy to come and deliver his lecture.
Good morning. You can hear me, right? Okay. So, thanks to Professor Krishnan and I used to come to aerospace engineering at ISC for a long time. Actually, many of you were not born. I'm not kidding. Okay, so people like Joga Rao, A.V. Krishnamurthy, you heard of A.K. Rao. Probably I say these names means nothing, but they were the very well-known aerospace engineers, and he was just a bacha, meaning a child. When he came as an assistant professor from IIT Madras, I remember. So, but anyway, I did come here, visit my visit to Indian Institute of Science continued with Professor Gopalakrishnan's invitations, and I was also kind of some holder of Satish Dhawan chair for. So, and then Professor Manohar and Devashish Roy, who is not here. I continue to come to ISC, either civil engineering or aerospace engineering. So the main thing is, I think I don't have to talk about myself, but my main areas are applied mechanics and computations. So what does it mean? So the applied mechanics is a very, very broad area. Everything under the sun belongs to mechanics, right? Whether it's bio, geo, anything, right? Fundamental understanding of any field is mechanics, right? So mechanics is really the source of many things, but how do you really get to the level of prediction? Because ultimately we have to design components or systems that are used in real world. So that means we have to develop mathematical models of the physics and then take to the next level of prediction, which is through only computations. Taking a course in mathematics is good, but it won't solve the real world problems because of the complexities of geometry, materials, as well as the couplings, nonlinear couplings between fluids and solids and even electromagnetics and so on. So what I'm trying to say is computational mechanics is playing a major role. So it is actually, I call it third pillar of engineering, investigation and research. When I say third, what are the other two? Mathematical model development, and second is experimentation. We need experiments for basic reason of characterizing the system and also validating computational models. So we must pay attention to all three pillars. So today's talk is dedicated to the very interesting topic I call dual mesh control domain method, which is nothing but a marriage of two well-known computational techniques. One is finite elements, which is dominating structural mechanics, and also it is used in Europe in fluid dynamics as well. But fluid dynamics is really mostly owned by finite volume technique. So I will say a few more words as I go into the lecture. But finite volume method, those who work in that area largely inherited all of the good and bad from the finite differences, because the same ideas are borrowed into finite volume. Only difference between the two, finite difference and finite volume, is finite volume uses the balance equations in an integral form, what we call a global form of the physical laws. And then it goes back and replaces the derivative using Taylor series expansions. And whereas in finite difference, you go straight to the differential equation, replace the derivatives in terms of the finite difference Taylor series formulas. Okay, so neither one has any way of minimizing the error, whereas finite elements is based on such concept, minimize. Okay, so let me go into the main thing is I want to talk about few comments related to role of computational mechanics, and very fitting for because mathematics is the language with which all of us engineers speak. So mathematics is given. It has to be there. So computing is what I'm trying to emphasize here. So I'll say a few words about that. Then I will go into the weak form Galerkin finite element method and then finite volume method in brief way using a typical two-dimensional boundary value problem. Okay. Then we'll talk about the actual dual mesh control domain method, which is nothing but taking the good of the two methods, and I'll explain what that is, and putting into one method that is as good as finite volume as well as finite elements. Okay, I'll show some numerical examples also. Then I'll close with some remarks. Okay, so, and this is my colleagues in the front row, please forgive me for saying this, but everything that we do as engineers, the model phenomena, physical phenomena. See, the word model is a very generic one. Model means represent the physical process with the help of the laws of physics or axioms or anything that can help us characterize the system in the form of differential, integral, algebraic equations. This is what we call mathematical model. Okay? So once you get there, you have set up equations. But how do you solve them on a complex domains with multiple couplings and also nonlinearities? So that is where the tools of mathematics only help you, but they don't solve it. See, separation of variables, for example. It's very good for only rectangular domains or circular domains. Otherwise, you cannot separate the spatial, two different or three different coordinates and also time. So we have to use numerical methods. And that is where the mathematical and computational models are coming in. So most important point I want to make in that second bullet is they're never exact. See, just because they're printed in the books, don't think of them as exact. Okay, because I told you the word model. Model is nothing but representing to the extent we understand the physics. We don't understand the entire physics either. So there is no such thing as an exact mathematical model. So as a result, the computational model would be as good as the mathematical model at the most, right? So, but it is never exact. But we know we are engineers. We want to solve the problem. We don't look for the so-called exact solution. So every time we attempt, we want to improve it with a hope to get there asymptotically. Okay? So the manageable solution that allows us to design and build it. That's what we need. And toward that goal, the computations come in. Okay? So the errors come in two different levels. First level is when you write the mathematical model, you make assumptions. So whether you realize or not, there are a lot of assumptions we make about the material behavior, for example, even geometries, the stimuli that is put on the system, right? And then second level is when you take the mathematical model to computational model, discretization, you introduce additional errors. So now we have to be very, very careful about having some estimate of these errors so that you can, with some level of confidence, you can say this is the amount of error I'm tolerating in our solution, because the design is based on your solutions, right? So the designer should know exactly what are the errors. Okay, so that will limit the performance of the system. So we only try to improve based on what has already been done. That is our research. Okay, remember what Newton said, right? Standing on the shoulders of people who have done already so that you can see further or farther. Okay, I always have this further and farther. By the way, if you Google, you have this, you can check whether it says further or farther. Okay, but both are okay, right? Further or farther is fine. Okay, so the third or last fourth bullet. So this is something I always communicate even with my colleagues. Today, this morning, when I walked in, we were talking about this. See, knowledge of the domain, what we call domain knowledge, domain expertise is very, very important. AI will not do it. ChatGPT will not do it. It can only depend on what is there, right? It is not intelligent enough to get the new ideas, new innovative things. It only can use what is there. In fact, it can even give you a reference, create a reference. But reference it will pick a title from somewhere, author from somewhere, and a volume number from somewhere, and it may not exist. Okay, so what I'm saying is you must have domain expertise. Without that, I'm not saying negatively. ChatGPT, AI are very good tools, very helpful. In fact, it helps professors more than students. You know why? You can already check this AI and ChatGPT before you go to professor. In fact, you can avoid going to the professor. Okay? So, what I'm trying to say is you can get a lot of help, especially language help when you write a paper. Okay? But don't copy. So, you try to learn from these. But anyway, I don't want to go too far into that. But what I'm trying to say is data science is limited. Okay? It is limited for two reasons. One, the data that is authenticated, meaning certified, comes only from two sources. One is experiments. Experimental data is very limited for two reasons again. One, most of the data, experimental data, is in industry. Industry does not want to share. Proprietary reason. And universities, how many people are in experiments? Compared to when I was a student. Today, it's even worse. Maybe 1 in 15 or 1 in 20 doing experiments. Because everybody is in a hurry to publish. And that is possible by doing numerics, right? Theoretical. Experimental, it really takes a lot of effort and time as well as money to set up, get results, and publish, right? So it is limited. The second way to get the data is through certified computational tools, such as finite elements and finite volume. So these are very, very useful even for AI. Okay, ChatGPT. Okay, so that means we can generate a lot of data using computational mechanics. And at the end, only two things matter in real world. One is reliable functionality of whatever that you are designing. And second, cost. And the cost element is not taught too much in our academics, right? We kind of leave it to the industry. We don't really, even though we may take a course in economics as an undergraduate, but we never ever really try to find what is the cost of producing an object, right? We are totally, unaware of the cost of the product to which we really trying to contribute our knowledge. But those are the only two things matter in the real world. Okay, with that, let me mention one other thing. There are many topics that are in commercial codes. Abacus, ANSYS, COMSOL, name it. All of these, CATIA for automobile, but all of those are based on research that was carried many, many years ago. And there are a lot of fixes. Okay, what I mean, fixes means in order for the computational scheme to perform, we created some knobs and twists, like artificial viscosity, upwinding, reduced integration, stabilization. All of these are artificial. I mean, of course, you can give some rationale, but we are problem solvers. We will somehow make the scheme to work. And this somehow is where we use these knobs and twists. But we need to slowly get them off, because it's like taking a medication for a disease. But medications do have side effects. So also the fixes. So we must understand what is the real issue in transferring a computational or mathematical model into computational model. Where is that we are losing? Why this is necessary to create a upwinding or artificial viscosity and so on. So that is where I'm getting it. So we need to improve our computational tools. Okay, so I'm trying to make a case for it. And the second, I think, especially young people, I've been telling that we don't have to be Einsteins or Newtons or Ramanujams, right? We can take pride in whatever little we do. In fact, this little we do, epsilons, the mathematical words, right? Epsilon stands for smallness. But we together, create an ocean of knowledge. So take pride, whatever little you do, feel good about it. Okay, so don't expect that you are going to be Einstein-like contribution. Of course, if you can, that's fine. Dream high. Okay, that's okay. It's not a sin. Okay, so now I want to just mention something about all numerical methods sharing some common features. So take finite elements. Okay, so discretization with some shapes. I'm only showing triangles, but they could be quadrilaterals. And then meshless method. So all these circles are what they call compact support for the interpolation functions used to derive the discrete equations. And then finite volume technique, also same thing, except the way they create the discrete equations going to be different. All these three methods ultimately lead to an equation that looks like Ku equal to F or Ax equal to B, right? So a coefficient matrix, a relationship between the two variables, which we call duality pair. So this is another very important concept a lot of people either don't know or don't understand. So nature has this cause and effect. Something causes for everything that you see. Okay? So a force applied on a system causes it to deform in a structural sense, right? So deformation is measured in terms of displacements. Okay, gradients of displacement is what we call strain, right? So this duality is very, very important. All K is doing is relating the U to F through algebraic relations. So at the end of any of these methods, you get only this. So if you look at from mathematical point of view, you're solving system of algebraic equations. Whether linear or non-linear, it doesn't matter. Okay? So what you see is at the end, everything that you did actually within the method is lost in the form of K. You only know there are certain fixed number of points. And we are trying to relate the values of the duality pairs at these points. Okay, and then we apply the boundary conditions, solve it. So this is the thing. You don't really know how you obtain, you know it, but it depends on the method. But at the end, you're all just paying attention to the points. Okay, so that is the mesh. And actually the meshless method is a misnomer. There is no such thing. Okay, there is no such thing as meshless method. It's a less method. Okay, all right. Only meshless method is classical variational methods, like Ritz method, Galerkin method, where there is no mesh. It's all parameters. Okay, so let me start with a second order boundary value problem, and where A11, A22 could be functions of position, and F is any external stimuli applied, and U is the variable that we want to determine. And I don't want to go into the details of explaining where it comes, but it is the most celebrated equation all of mathematical physics, known as generalized Poisson equation. It comes in heat transfer, it comes in fluid mechanics, it comes in structures, name it. So if we were to solve that in finite elements, what we do, we take the function and approximate it over any typical element as a series of unknown nodal values and known functions. And I'm just showing here that mesh and a typical element, if you think of in terms of a structure, element is there with some thickness because this is a 2D, and the solution on that element is the surface. That is the actual solution that we are seeking. But in finite elements, we can replace that surface by, if it is a linear interpolation, it would be a plane. If it is a quadratic, another surface, cubic, higher order, right? So, and as you go in the interpolation degree, you will hopefully getting close to the actual representation of the surface, which is the solution to the bound value problem. Okay, so in some ways, how do we really approximate to satisfy the governing differential equation? We substitute that into the equation, but when we substitute, only this part is going to change, and it is approximation, so this will be not going to be exactly equal to F, right? This is obvious, because F is something given, and I replace the actual one with some approximate one. So this difference is the residual. So our goal is to make the residual minimize somehow. How you minimize can be any number of ways, and that is where different methods differ from each other. So in finite elements, you could think of taking the residual and making it zero on a typical element. So I want you to think at this moment, what is R having inside? It has these unknown nodal values. And just to fix your thinking, think of triangle with 3 nodes. That means there are 3 unknowns, 3 nodal values. And this equation will give only one equation in 3 nodal values. So it's useless. We need 3, right? So what do? You may want to subdivide it. See? By the way, you don't see this in any books or papers. But so that means you have to take the original triangle and subdivide into 3 triangles, apply this equation in each of them, because we need 3 equations. The other way is to use the original one, but you use the weighted integral statement. See, this is not weighted integral. So we create this weighted integral form, which is called weak form, and there for every arbitrary function from the same vector space, this equation holds. Okay? So whether, Hilbert space of order 1 or 2, whatever that is. So it has to be dictated by the actual differential equation. In this case, H1, the Hilbert space of order 1 will do the job. Okay? So it could be triangle or rectangle or quadrilateral. Okay, so at the end of the day, finite elements, I'm not going to go into the detail, but you all know the finite element equation looks like this at the element level. Ku equal to F, but F is into 2 parts because one F comes from the actual stimuli that is specified. The second one comes because of the boundary flux, which we don't know, because you took a continuum out of the whole, so you have to display the flux that goes into the neighboring elements, which will not be known until you assemble. When you assemble, you don't have to know it because it cancels. Okay? So that's the idea of assembly. So then finite volume method is slightly different. First, pay attention to the fact that we also create a mesh, which is, again, I'm showing the rectangular grid but it's general. Okay, this is not a typical control volume. People, typical control volume is very structured grid. Okay, so anyway, I'm giving the benefit of that you can make a unstructured grid, but where do they satisfy the differential equation is different. So this yellow is called control volume. Okay, so I don't like the word volume for obvious reason. In a 2D, it is not a volume, so that's why I replaced with domain, word domain. Okay, so the differential equation is satisfied on this domain, not on these elements. That is what finite element method does. Okay, so, and I'm just showing a typical rectangular mesh. So these are the four such, if you look at this one, this is exactly these four elements, but this is the control domain. So let me show the differential equation. So if you take the differential equation and then you can integrate once, because it has d dx of a11 du dx. So I can integrate once using Green-Gauss theorem. So I get only boundary integral except for the f part. So you see the finite volume has a very nice thing. It reduces one dimension. I don't have to evaluate domain integrals other than for this f. So there is a saving, right? And domain integral also, finite volume people make gross approximation. They say no matter how f is varying spatially, they replace it with average value. So they never evaluate the integral. So that's why they use lots of so-called control volumes. So brute force, because they see that speed goes up. They have no integration at all because they replace these derivatives also with Taylor series. So there is no integration in finite volume. Okay? All right. So now what is dual mesh doing? It's exactly same as finite volume, okay, not finite elements. Only difference is this mesh, which is common in finite elements and finite volume, is also used in the dual mesh because they are the one which has the interpolation. Elements have interpolation. Control domain has no interpolation. Okay, so then I use the same as finite volume method over that control domain, which I'm same as control volume. I evaluate the integral, but I do not use Taylor series. I use finite element interpolation because I have them. So you remember the finite volume people, finite difference people don't have concept of interpolation. You can interpret the Taylor series as interpolation, but it is not. You are replacing the derivatives with the quotient, right? So here, since I have interpolation, I can differentiate the field variable. I can get du dx, du dy, no problem. So I don't have to go to Taylor series. Okay? And second, since they are interpolation functions, I can evaluate integrals. But now, because I'm using finite volume concept, I evaluate integrals only in 1D for 2D problem because it's only on the boundary of the control domain. Okay? So you can see, so I'm showing right now, after evaluating that using Green-Gauss theorem, this derivative is going to come from the interpolation function because UH equal to summation of UJ psi j, right? So I can differentiate. So I brought the interpolation from finite elements. Okay? So now everything could be very modular. Unlike finite volume people. Oh, you have to really go look at the literature. By the way, this baby was born during COVID time. How? Because I was stuck at home. And I was wondering what is this finite volume people are claiming superiority over finite elements, in fluid dynamics at least. So I wanted to know. So I studied, and then I figured out that they don't have two important things missing. One, no concept of interpolation. Second, no duality idea. They just, every time they see du dx, du dy, they rush to replace it. But du dx is a physical variable, flux. So if it is on the boundary, if I know flux, I don't have to know the temperature. If I know the temperature, I don't need to know the flux. So there is never a need to replace the derivative because it's an entity. It's the secondary variable, dual variable. So I bring both of those into this dual mesh control domain method. Okay, so here again, I don't want you to read too much. So this is the global balance law of elasticity. See, this is the nice thing about finite volume method because it uses the physical law directly. No weighted integral statement. But the only thing is they don't have concept of interpolation or duality. So this Ti is a dual variable. It is the traction. See, I should not think of replacing it with some derivatives, okay? So, and this is the body force. So I'm showing when I replace Ti using the Cauchy's formula, you get this expression. Then you can use the constitutive law to replace the stress tensor components in terms of the strains in terms of displacement gradients. All of that they do and I do. Only difference is their gradients are replaced with Taylor series. Here they are replaced with the interpolation derivatives. Okay? So we do reduce the dimension by 1. Okay? So another thing that we brought as I got into, so during this COVID time, I actually was programming. I started with 1D and then I did 2D. Then I said, okay, I don't want to publish every paper just me. So I started bringing my students in there. So only paper I published is the concept by myself. Then my students took over and they started running, applying to different, heat transfer, fluid dynamics, elasticity, plate bending, and so on. So there are many papers that are, and in fact, a new paper coming in the Journal of Computational Physics on fluid dynamics. So you can see the two elasticity equations written just as integral statements on the boundary of the element, control domain. Okay, not the boundary of the element, control domain rather. And so, by the way, let me go back here. See, in many real world problems, there are no body forces. So you never really, these integrals, even though I put them there for completeness, we don't really have body forces because they are usually, unless you are taking some gravitational force or something. But if it is there, no problem. You just evaluate the integrals using numerical integration. Okay, so, and see the beauty of this, all of this, by bringing interpolation, it is all taken over by now numerical integration. Okay, so these are the transformations. Everything is in finite elements. So if you look at the control volume, that is control domain rather, portion, the control domain is actually here because it's on 4 different elements. So when you look at a typical element, it will have contributions from the different nodes to that, from that element to different nodes. So we calculate element wise. So this is another thing we did in later years because now we brought entire structure as infinite elements. That means we create the discrete equations element wise. So everything, assembly, solving, everything became finite elements now. So this is modular. There is no more intervention as a human being. This is what finite volume people doing. See, very difficult to duplicate somebody's results in finite volume method. Unless you call the person or write that person, what did you do? Because behind the scenes, they are doing some mumbo jumbo in terms of evaluating integrals. And they even created some ad hoc schemes. All of this came from the baggage from finite difference people. See, they were doing the same thing there. Okay? So, for example, when you go to the boundary nodes, if you have to put the center difference for the second order derivative, you will get a fictitious node. So what they do? Oh, I'll use backward here. So that means they switched the actual interpolation, order of interpolation, because center difference is second order accurate. So forward or backward is only first order accurate. So they introduce error. In this method, you never have to replace them, because either you must know the nodal value there. If you know it, then that node doesn't play any role. It only plays role in post computation. If it is not known, you know the flux. You must know the flux. You cannot say, I don't know. Then you don't know. The physical problem must know. Boundary conditions should be one or the other. You cannot say, I don't know. Okay, right? So I think a lot of good things happen, and I won't go into the details, but very, very powerful technique came out of the marriage of these two. And so in summary, I must say the marriage is to borrow the concept of finite control volume. Okay, no weighted integral statement. Take balance equation directly. Okay, and it converts the domain integral into boundary integral. So there is a saving there. But then we bring the interpolation. Once you bring the concept of interpolation, a lot of things become finite element-like thing. Everything is in terms of element equations, assembly, imposition of boundary conditions, even nonlinearities, everything is very, very straightforward. Unlike in finite volume, they replace the nonlinearities very crude way, because they want to do everything without integration. See, here we don't. If nonlinearity is there, we evaluate integrals including the nonlinearity. Okay? All right, so sorry. This is the first problem. Plate with a hole, standard. By the way, it's not an unsolved problem, just to compare. And this particular problem has a solution, analytical, not exact solution. Remember, there is a difference between phrase analytical solution and exact. So analytical means you didn't use any computational method. Okay, you found some way to come up with the solution using, the techniques of the mathematics. But exact solution means you really solve the equations exactly. So analytical, you may be doing some approximation, okay, to get analytical solution. So here the solution exists for infinite plate with a hole. That's the only problem where you can solve analytically. But that is not the case here. It's finite. So don't expect the finite element or finite volume solution to be same as the analytical solution, because analytical solution is for an infinite plate. Okay. All right. So we use the biaxial symmetry and use the one quadrant. You can see the elements are very skewed, so you don't have to use regular mesh. And so the results are presented here for the dual mesh here and finite elements here. Of course, by looking at it, it's not much difference. I'll show you in terms of plots. And this is for the stresses, very similar, very good comparison graphically. But here are the results. Okay, so you can see the dimensionless hoop stress. Okay, that means radial stress. Here is the both finite elements and dual mesh, they give exactly same solution. Okay, so you remember that. You might say, oh, then what is the benefit of using dual mesh? But you have to remember there is a less computational time, because finite elements, you have to evaluate all of the domain integrals, not boundary integrals. Okay, and there are problems where finite element won't give exact same solution as dual mesh. All right, but especially axisymmetric problems, dual mesh gives exact analytical solution. I mean, this is something, if any of you in mathematically oriented, you should take up that and prove why. Okay, but so we found it. And here is a problem with a crack. And of course, so, and singularity is at this point O. And so the analytical solution for this with a crack is written in terms of the distance from that crack tip to any arbitrary point in the domain. And it is the stresses would be 1 over square root of R singularity. Okay, so you can, and here are the solutions again. So you can see the displacement in the y direction, okay, and they're exactly matching with each other, dual mesh and finite elements, and same thing for the stress. Beautiful, right? And you might say, what about finite volume? Well, finite volume, people really, if you really try to do everything like what I'm doing in dual mesh, you can show it will give you the same solution. But when you replace with the derivatives, there would be discrepancies because you're not supposed to replace the secondary variables with the derivative Taylor series expansion. So then we extended to nonlinear problems with arbitrary meshes, and we applied this Newton's method. See, all of these become very standard because finite elements already has this. There is nothing new. So since we have adopted interpolation, we use all of the ideas from finite elements with regard to implementation. So here is a cylinder, hollow cylinder. And so this is a cooked up problem, what you call, if you use a certain kind of nonlinearity, we can manufacture the solution, okay, by substituting assumed solution into this. And this is the assumed solution, analytical solution, sorry, not assumed, analytical solution for the temperature. K is the conductivity, and it comes in terms of the positive root of this expression. And so we compared these results with using bilinear elements and also biquadratic elements. Okay, see, all of this is very standard now. So just imagine if it is finite volume. They have to change from linear interpolation to quadratic. They cannot use these words, linear and quadratic, because they have to go to different level of finite different Taylor series expansion. Okay, so all of this became very standard. So you see the benefit of this idea. We are really exploiting nice features of FEM, and at the same time, nice features of the finite volume. The two nice features of finite volume, I want to give the credit where it is due. One is the using the balance equations directly, no weighted integral. So this has the implication when you have shock waves, shocks, large gradients. In finite volume, they tend to smear it because you're multiplying with a weight function. Here it doesn't. We are not multiplying. And second, it is reducing the dimension because we are using Green-Gauss theorem to write the domain integral in terms of boundary integral. Okay? And then rest is all finite elements because of interpolation. So here again, linear, nonlinear, they really come very close. There is, you cannot see the difference other than in fourth decimal. So the solutions are very, very good. So we then extended to incompressible, viscous incompressible flows. And this is actually more recent work with Navier-Stokes equations. That means including nonlinearities. Okay, so again, all of this detail you don't have to, at the end, you will have this equation. By the way, now it is unsteady also. Okay, so the mass matrix, here is the velocity. This is U itself is velocity, U dot is the acceleration. Because in fluid dynamics, velocity is the degree of freedom. Okay. So the reason, it's not that I'm advertising my books. So this also came during the COVID because one of my colleagues who works, he teaches finite volume technique, okay, N.K. Anand. So he said, oh, Jay, and I want to write a book with you. I said, I don't know enough about finite volume. They said, okay, we'll do it together. But I was already into this studying the finite volume during this COVID. So I was able to even make some changes. I don't want to say too much, but I figured out some of the things they were doing wrong. I told him this is not right because they called zero thickness control volume. It's nothing but finite forward difference. See, this is the kind of jargon they create. Okay, and they don't look at very closely what is the resulting scheme. And I showed it is same as forward difference. So why are you calling zero thickness? Okay, so things like that. Anyway, many of the ideas related to nonlinear finite elements is in my nonlinear FEM book. And Professor Manohar, is that book available now in India?
Nonlinear?
Yes.
Indian edition, I'm not sure.
But it's still expensive. Yeah, okay. The linear is available, very cheap, $10 or less than that. Okay, so this is by the way, cavity, wall-driven cavity is the most commonly used, what you call benchmark problem. So the three walls are fixed. There is a viscous fluid inside, and the lid is moving from left to right with a, say, unit velocity. Of course, all non-dimensionalized problem. So if this U is increased to large number, that means the Reynolds number will increase. Okay. So this is just, I'm showing you as an example here. So you can see the corners will have a singularity, correct? Because we are saying U is equal to 1 from this side, but from this side, U and V are 0. So, and that is where your real world thinking has to come. What exactly is happening? Think of a belt going over this cavity. Okay, I mean, you're running a motor and belt is moving. So the viscous particle stuck to the belt just from 0 plus. If this coordinate here is 0, 0 plus is where the belt, it is on the belt. But here it is not, right? So you have to, tan hyperbolic function can describe the boundary conditions very nicely. Okay, go to 0, right at these points. But anyway, we did study with U equal to 1 here, U equal to 0 also, at the end points. And that's the benefit you have with computational methods. You can try all kinds of things realistically and so the mesh shown here is very, very refined, 86 by 86 mesh of bilinear quadrilateral elements, resulting in 7,569 nodes. And refinement, of course, it's a non-uniform mesh because the boundary layer, develops along these boundaries. So just think of human being. If you have to run around a square, what do? Your tendency is to cut the corners, isn't it? Right? So the fluid also does the same thing. It tries to, if this has to move slowly, then it will go there and come down. But if it is moving fast, it won't go all the way here. It will try to confine the flow to the inside. Since they are viscous particles, the particles here are connected to the other particles here by viscosity. They are stuck to each other. So then they create their own inside what you call secondary flows, depending upon the speed of this. If the speed is very low, there is no secondary flows. Okay? And so you can see this is 10,000 Reynolds number, very large number. So you can see the secondary flows. And we compared this with the finite difference, third order accurate scheme. They had to use the 256 by 256 cells. Okay, so we can see 4 times more and 16 times actually if we square it. So we compared with them. So this is the same. This is taken from the paper of Gia and we compared. So this is indeed here. So the one-to-one correspondence you can see. So we were able to capture all of these, even third. So not only secondary flows, there are additional. As the speed increases, you will get more. And suppose you make this cavity to be very narrow rectangular channel. What happens? then it will break. It will, along the height of the channel, there would be many recirculation zones. And that's exactly what happens in the countries where cold and hot are equally there. They have double glazed windows with a small gap, very infinitesimal gap, because that is how you protect loss of energy. Okay, so the fluid, which is air in this case, which is inside, it will recirculate there and create a boundary layer to insulate. Okay, so these are benchmark problems because they can be used for anything, including flow around buildings and a flow around airfoil. Right? All you need is stick another object here. Right? So all of these can be studied with these benchmark problems. I do have one of those here, see? So you can think of this is circular cylinder here, but you can put aircraft cross section. Okay? So the flow is coming from here and goes over the body. So here is the mesh, and you can see, and this is enlarged. So the flow, you can see how it develops. If you really think this is an aircraft, the vortices developed and they diffuse only after a finite distance, so that the next aircraft should not take off until this influence is gone, totally diffused, right? And in addition, this could be looked upon as a building, tall building, air flow around the building. So if there are multiple buildings, they are going to create a wind tunnel effect. All of this can be studied with this, right? So when it looks like academically, oh, it's what is this problem? Why I'm interested in this? There are a lot of applications real world. It could be even food industry, mixing of different species, okay, masala, right, or spaghetti. So, but you have to bring the right constitutive equation, right species equations, okay. So anything can be done, but it has to have right mathematical model. Okay, so, and this is what they call step. That means there is a small opening here, rest of this is fixed wall. So the flow comes in here and goes through, you can see that. So they call backward step problem. This is also very commonly used benchmark problem for studying or investigating the accuracy of any new computational scheme that you develop. So this is the dynamics. So you can see at any point you can look at the flow pattern, and this is the velocity pattern at x equal to 7 along this. So you can see this is compared with the finite element solution in this book that I have written with Gottling has that solution. Okay, so I want to just not take too long, but I wanted to give you the general idea of the method. There is a lot you can read, but I wanted to give you the idea of the dual mesh control domain, how it relates to the two most popular methods. It satisfies the global form. This is the main feature that comes from the finite volume. And it uses two different meshes. That's a dual mesh means one mesh is to discretize the domain. And discretization brings with it interpolation. Okay. The second mesh is intersecting mesh. And that mesh is where the governing differential equation is satisfied in global form. In finite elements, governing equation is satisfied element-wise. Here it is not. Okay. So another important thing is the dual variables are always inside the elements. In finite elements, post-computation has a problem because the derivatives along the interface of elements are not continuous. Here that is not coming into picture. Okay. So, and the primary variables have specific fixed type of approximation. Okay, so this is the interpolation coming from finite elements. And physically consistent boundary conditions. So we don't replace the derivatives in blind way. We only replace inside the domain using interpolation, not Taylor series. On the boundary, they are never replaced. The derivatives or fluxes. So you must know the flux or temperature as an example. Okay, so there is no discontinuity of secondary variables like in finite elements because we are not computing them at the element interfaces. They are along the boundary of the dual mesh. And it is less computational effort because we reduce the 2D into 1D, 3D into 2D. Okay. All right. So I think extension to inelasticity or plasticity is coming. And you can take, and this is where I think we will have much major contribution, fluid structure interaction, because it is a problem where same method can be used for fluid and solid. So most people who use fluid structure interaction, they use finite elements for structure and the finite volume for fluids. But the concept of velocity in two is not the same because Eulerian description is used for the fluid mechanics. Lagrangian description is used for solid mechanics. What is velocity is time derivative of the material location, the instantaneous location. Okay, dx dt, small x, is the instantaneous location. Whereas in structural mechanics, du dt is the acceleration, velocity. Okay, so that is, I think, a lot of people don't distinguish because they're studying very slow flows. With a high speed flow, you will see the difference. And also, if the structure is deforming, then you are in big trouble. So people like Farahat, at Stanford, all of, if you read their papers, when it comes to this interface, they're playing games. It's just a very, very crude approximation. So it is a very critical region. Making crude approximation will influence the results. So you have to be very careful about that. So I think it's a very good area. So both plasticity and fluid structure interaction. And this, we have a paper coming out in the International Journal of Numerical Methods soon on plasticity. So we have not attempted this yet. Investigate the mathematical aspects such as the error estimates. So there are a lot of papers on finite elements error estimation. The whole French school of mathematics, you can see, but I think there is a challenge in the dual mesh because we don't have quadratic functional. See, finite volume method doesn't use quadratic function. It's using governing differential equation. Finite elements uses the weak form from which you can construct the quadratic forms. So this is much more challenging, but it is a very useful topic area for those who are in applied math. Okay, so I want to acknowledge my co-authors. Tanmay is my PhD student, and he has worked on several of these papers. There are a couple of other papers already out. So this is coming, and it actually just came out, yeah. And this is in review for Journal of Computational Physics. The last results I showed for the flow is right in this paper. So if you want any of these, I'll be happy to. So this book actually came during that period, and I can use finite difference, finite elements, finite volume, and dual mesh. All of them are in one place. You don't have to go to another book to compare or see the results of various methods. And of course, I want to thank Dr. Gopalakrishna and also Krishna. Word Krishna is there. What? Dr. Raghavendra, thank you for arranging the talk. And I will be happy to answer any questions. Any detail or anything that you want to know. Okay? I hope I didn't take too much time. All right. So you have to ask questions.
So, Jay,
Yeah, please.
how fast can you, computationally is the biggest advantage.
Right. So I think, this is a kind of a relative, it depends on how many elements you're using, right? So if it is two-dimensional element integrals, if you have a lot of, 100,000 elements, then a lot of computational time is going to go into it, right? Whereas the line integration is very fast, okay? So it's really depends on the problem. But there is significant, especially if it is nonlinear problems, okay?
Just a quick question on, so you do have the same issue with interpolation, locking, and other.
Excellent question. Yeah. So, remember, I think, when we think of all these methods don't bring locking. It's the interpolation that brings locking. What I mean is, when you don't use, I always give kind of Dr. Manohar knows, if you really have two or more variables in a problem, and those variables are not the same. It's not like elasticity where all variables are displacements. Suppose you have a mixed formulation of the elasticity. Then you have stresses and displacements. And they are not same, right? What I mean is displacements are higher degree differentiable field compared to stresses. Stresses need only one derivative according to equations of equilibrium, whereas the Navier's equations of elasticity require two derivatives. So if you say I'm going to use same degree of interpolation for stress and displacement, then they don't join. This is where locking comes from. So by using higher order interpolation, we get rid of the locking. But locking, it is nothing to do with the method. It has to do with the interpolation. So we practice the same. That means we use different interpolation in dual mesh. We don't use same interpolation. If you use same interpolation and lower order, locking will come. There is nothing you can do about it because you are not doing justice. See, it's like having a buffet. Buffet means you use a lot of food and people eat according to their stomach. That means higher order, big people eat more, less people who are lean, they don't eat. But suppose you restrict, everybody has to eat only this much food, then the people with a big stomach will starve. And that's what happens when you use equal interpolation and lower order. And that is when the locking is the most. So this is well-known fact. So if you use, even in FEM, use a higher order interpolation, there is no locking. But real world problem, people say, oh, I don't want to use higher order elements. See, this is a short-sightedness. If you really want accuracy, you have to pay for it. And paying these days is what? Electricity. No big deal, right? So I think people should have right understanding of things. Should not blindly think, oh, I want. So you cannot have cake and eat not, and same time you want to eat it. What I mean is you want to show the cake and you want to eat it. It cannot happen, right? So you have to eat it. You have to cut the cake, right? Okay, so, sorry. So what I'm saying, the locking will be there unless you use mitigating things like higher order interpolation. Yes. Well, I'm coming there, okay, please. Yeah.
So my question is this, clearly, there's a gap. I'm not writing papers on this book. I will read it. It's very interesting. But you're talking of Eulerian and Lagrangian approaches. They're separate ways. All the, how you set up the problem, everything is. So how do they come together in this? Because you have dual measure.
You're talking about fluid structure interaction. Yeah. So, okay, I think this again begs for me to explain the physics, because physics is where we have to pay attention. Computations follow it. So physics is you have to write where is the difference between the two field problems, fluid mechanics and solids. It is in constitutive equations. Because fluid mechanics relates the stress to velocity gradient, whereas in solid mechanics, it relates to displacement gradient. So your constitutive equations are rate dependent, there is no problem. Okay, so that is where the problem comes. If you don't use rate-dependent constitutive equations in solid mechanics, then you have to convert the velocity into displacement relations in a consistent way, meaning material time derivative, okay, which is going to bring nonlinearity automatically. Additional nonlinearity in addition to whatever constitutive nonlinearity is there. Okay, so the physics requires you to either use same description, which is say Eulerian description for even solid mechanics, which is a bit complicated, or you must bring rate dependent constitutive equations so that your field variables are velocities, not displacements.
Thank you, thank you for a very nice talk. I have two questions. The first one is, I see that this method has some similarity to the discontinuous Galerkian method. Again, in discontinuous Galerkian, at the numerical boundaries, right, you impose fluxes, numerical fluxes like finite volume. To overcome that, people have come up with these flux reconstruction schemes where the numerical fluxes are also modeled based on these interpolating functions, right? So how is your method different from the FR?
So I know your work. I mean, when you talked to me in my office other day, so I think again these are different issues, but we need to pay attention to in the case of transient problems, right? So time stepping, whether it is a half time, full time, all of these. I mean, when I say stepping, so those we have not gone. This is a very standard transient analysis where there is only a single time step. So if you want to bring accuracy and increase the speed, that's where your work can be useful. So we have not done. Let's talk about it.
Okay.
And when I say talk about it, means you do the work.
Sure. Yeah, I'm happy to do that.
Yeah. So I'm serious.
Yeah.
I want to help, but I cannot take your problem and put my student on it.
Sure.
Because they're already occupied with other topics.
Right.
But so once it gets to a level, then they can adopt it in their work.
Right.
Okay.
So my next question is, when you were doing these numerical experiments, did you find any gain in terms of stability constraint, right? So with respect to standard finite element, finite volume, and this dual mesh method. So does it bring any relaxed stability constraints when compared to the other two?
Yeah. So, okay, there are only certain problems where you can mostly linear problems where you have some handle on comparison. So once you go to nonlinear range, then there is nothing other than what you call manufactured solution.
Yes.
Okay, so manufactured solution is what we used in a couple of problems, because that is the one way to get confidence on your numerical technique. But if it is a real world problem, like high speed flow around an airfoil, so you have to depend on little bit on experimental.
Yes.
So that is where I say you need experiments for two reasons. One is to characterize the material, whether it's a Newtonian fluid or non-Newtonian, and second is to have validation. Right.
Yeah, so what I meant was when you ran this flow past cylinder case, a transient case, so were you able to run with a much larger time step for a given mesh with the dual mesh when compared to the other methods, which would blow up in some sense?
Yeah. So, okay, remember we have to adopt explicit or implicit. That is again another issue. So we have to use explicit for speed. And that is where some techniques that you are working on can be useful. So here we use the standard one time step, explicit formulation. All we need to do is to reduce the time step to get the accuracy. Okay.
They are all comparable for all the three methods?
Yeah.
Okay. Thank you.
Yes, it's a naive question. So actually, could you tell me something about so most of the literature that we study are related to either solid mechanics or fluid mechanics for these numerical methods. But how about there are other constitutive models such as higher gradient models or non-local continuum models where there are complications such as we have to specify both displacement and the flux at the boundary, or the displacement and the traction sometimes. So the literature or anything.
So, okay, I think I remember Gopalakrishna, and we talked about it sometimes. All of the higher order theories, including my third order theory, they bring higher derivatives, and that requires variationally consistent way. We have to know also boundary conditions on higher order derivatives or on their duals. So what we do, conveniently, we put this under the rug, so to speak. We assume the dual variables are zero. Dual variables for the higher order terms, like coupled stress. You understand what I'm saying? Coupled stress terms. Okay, just think about reality. How do you know this higher order components like coupled stress in real world? We don't. We only know, for example, whether stress is there. I mean, by saying that you fix it, then you know that stress would be generated, right? But how do you know if there is a higher order stress also, right? So what we do, I'm saying the reality. I don't know myself if there is a way to find out. There is no. Experimentally also, because first you have to know how to measure these things. So what we do, we assume the secondary variables are zero. Okay. So going back to this higher order derivative means in your formulation. Oh, by the way, one more thing I did not mention. Thank you for asking this question. Dual mesh control domain or finite volume methods work only for second order equations. That means if you have fourth order equation, you have to rewrite them as set of second order equations. Okay? You cannot see. Remember I said integration by parts. If you have fourth derivative, integration by parts is only once. Then you have third order derivative. So it's no good, right? So you have to rewrite them as pairs of second order equations.
For now, the most convenient method remains the finite difference method for these kind of things.
I don't want to use the word convenience, okay? Because convenience is not the end of the world, right? Because we want the real, physical, meaningful response, okay? So just because mathematics presents difficulty, don't give up. Mathematics is to help us. The mathematics that doesn't help, we throw it out. So what I'm trying to say is, if you have a higher order problems, you have to bring secondary variables that are, additional variables. Like derivatives themselves become primary variables, correct? So it's not a problem. Okay, so these are called mixed methods. Okay, we have done that. In fact, my PhD thesis was on mixed finite element approximations. So, okay, yes.
Okay. Hello, sir. So I want to ask, is your approach, with your approach, can we achieve a high order accuracy? Like, for example, in finite volume method, if you want to achieve high order accuracy, so we basically increase the size of stencil. So something like that, is it possible with your approach?
I didn't get it. In finite volume, what do you do?
Like in finite volume, if you want to achieve a high order accuracy, we actually increase the size of stencil, or like by stencil I mean the neighboring.
I know what you stencil. Yeah, I mean, by the way, we have also stencils here, because if you use the 4 elements, these 9 nodes are there, whereas the finite volume gives only vertical and horizontal. Dual mesh brings all 9 nodes. This is another important thing. If it is a finite volume, it only brings the 3 vertical, 3 horizontal. The other corner nodes don't participate the way finite volume works. But anyway, if you need to bring them close or whatever, it's like refining the mesh. It can be done.
Yes, means we can refine the mesh, but like what we want to increase the order of accuracy, like to go to third order or fourth order accuracy.
Yeah, so, okay, very good. So if you want to increase, just take the center difference. We have 3 points in 1D, right? If you increase the interpolation, it becomes 5 points, 7 points, and so on. Your stencil is going to increase in number of nodes.
Okay.
So the bandwidth also increases. But bandwidth is not an issue these days, because we don't necessarily use Gauss elimination. We use the Gauss iteration, Gauss-seidel, right? So it's not an issue. But I'm saying is you can increase the finite volume order in terms of the what do you call it, Taylor series expansion. So you remember one thing, any order derivative can be expanded to any higher order stencil. That means you can have only 2 nodes, you can have 3 nodes, 5 nodes, 7 nodes, because the order of accuracy increasing. But you also paying for it because there are more nodes coming into picture.
Okay.
Right?
Okay. Sir, like basically in your approach, if you want to go to the high order accuracy, so like we need to increase the order of interpolating polynomials.
Right. So, okay. So the main thing, just in simple way, we are not using Taylor series. It's only interpolation. So even though we typically talk in finite elements about linear and quadratic, but it's not the end of it. You can have any degree of interpolation.
Yes.
You can go to P, where P could be 6 or 7 or 8. Okay. So that I do in shells. We call them spectral interpolation functions, higher order. Okay. So you can do the same thing here. So now you gave me another idea, right? So we should be, so maybe, some of you should take up because I have so much to do on my plate. So, I'm serious, but I'll be happy to help you. You don't have to put my name. Okay. All right.
And sir, one more question. So, like, suppose if we have a shock wave within a control domain. So, okay, so like means now if you want to handle the shock wave, how are you calculating derivatives?
Yeah. Okay. So, this is a very physically interesting. When we say shock, see, there is no discontinuity in real world. It's only sharp. So the degree of sharpness, we say it is discontinuous. There is nothing discontinuous about it. So that means you have to, any kind of advection flows, you have to create a mesh very refined near to the large gradient. Even if you use the linear interpolation, you have to use lots of nodes near that sharp so that it can actually take that, instead of going diagonally and smear the crack or the speed of the shock, you have to refine the mesh. So there is a physics that kind of begs for what you call refined or local mesh refinements to capture the physics. So you cannot, you saw that in the case of cavity, we had to refine the mesh along the, as I go in higher order, higher Reynolds number, the boundary layer thickness is going to be 1 over square root of the Reynolds number.
Yes.
So it gets thinner and thinner. That means you have to capture the boundary layer thickness by at least 1 row of elements. And maybe 2 is better. So what I'm saying is physics is asking for something you cannot overlook. If you are very stubborn and say, I want to only use this, that is the amount of accuracy you will get. So you have to really, again, real world problems require you to use the right kind of mesh to get useful results. It's not like publishing a paper, but really you want to see, is this response reasonably correct? And hopefully there is somebody who is doing experiment also to help us, right?
Thank you.
Okay, one more hand. Yeah. Oh.
All right. Hi. You showed us a simulation of flow past a cylinder, I think.
Right.
The boundary to the right was an open boundary. Can you say something about how the open boundary is implemented? And
you talking about the dimensions?
No, there's an outflow boundary condition.
Yeah. Okay. So the inflow is of course specified velocity. Okay. In this case, we use a uniform. Okay. If you want to put fully developed flow as input, is okay too. The outflow is stress-free. Okay. You understand? So that means I don't specify velocities. Right? Stress-free means that gradients are 0 because it's fully developed. So that dictates, I have to qualify That means you have to be far away from the cylinder
Right.
to realize that. The physics dictates that. If you're too close to it, it won't be free.
Is there a way to implement the Sommerfeld radiation boundary conditions more? Is there a more natural way? Does implementing the radiation boundary condition become more natural in this?
Yeah, typically 10 diameters.
Okay. So you do have to push the boundary far enough downstream before you can.
Yes. The same thing with the vertical also. Yeah. So again, these are coming from experience with doing the simulations and having some experimental validation. So the effect of the boundary would be felt if you're too close. Saint Venant's principle applies even in fluid dynamics.
So I just wanted to ask, so can this method completely replace FEM for problems in solid mechanics, or are there problems where FEM would perform better than this method?
Okay, this is a tough question. Okay, there are people always coming up with all kinds of methods, particle in particle, this and that. So all of these have certain kind of specialty. So when I mentioned finite elements dominating structures, that is true. Same finite volume dominating fluid mechanics is true. So there may be very small number of specialized methods in both areas. So, but those don't seem to come to the surface in terms of real world. Okay, I mean, maybe people publish papers and show something, but it would be only for that problem. So I think that is a danger of selling something as by showing it is very good for some problem and kind of generalizing it is good for everything is not right. So we have to study. So like Boltzmann method, that a lot of people use in fluid dynamics, right? But if you really ask them, more serious questions about Reynolds numbers, all that, then they say, oh no, this is the only for this range of Reynolds number I can use, right? So I think anything that involves physics correctly. Physics means the equation that represent the physics. Again, I already mentioned no equation is exact. Okay, so given for example, Navier-Stokes equation is not exact actually. Okay, there are a lot of assumptions made. In fact, I will get a little more philosophical here. Who said that any field variable is differentiable even? Who said that? Only because our continuum mechanics said that. Continuum mechanics, we endowed all the field variables to be differentiable so that I can take a limit. But if you're talking about particle level interactions, that is not true, right? So when you take the limit, it is going from one particle to the other. It's not the same thing, right? So what I'm saying is within the continuum assumptions, the equations that we are dealing with, they do require differentiability. Okay, so I think you have to really feel and study consistent with what is the goal of your study. Okay, so most of the real world problems we made tremendous contributions and advances by using continuum approach. Okay, so but continuum mechanics is not for everything. No, even in nanofluids, we are using continuum equations by kind of making assumptions. Okay, same carbon nanotube. People use shell theories, cylindrical, So, but all of these, kind of continuum theories, whereas a carbon nanotube is all atom interaction, right? Potentials. So really you should use molecular dynamics. So what I'm saying is, in a short answer to this, you have two things. What is the goal of your study? Depending on that, you pick your mathematical model. Then, based on that, you pick the numerical method. Okay? All right. Thank you. I think I have, maybe this is a relatively record number of questions I had because it gives me more satisfaction that you did pay attention to my talk. Thank you. I was hoping that there would be a question from Professor Manohar. So,
I have a lot of questions, but I'll ask you.
okay, all right. So this is okay, having a lot of questions instead of one question. All right.
So we all had an excellent talk and a great interaction for the last 1.5 hours. So we should really thank Professor J. Reddy for taking time off and coming and speaking to all of us here at an IAC. So I request Professor S. Gopalakrishnan to hand over a token of appreciation and also gratitude for coming here and then delivering this lecture.
So that's last message. All right. All right. Thank you.
We would also like to thank Professor Anant Ramaswamy, Chair Civil Department, IAC, for all the support, in fact, through this park and also through himself, where he actually helped us to connect to a lot of people here. And then a lot of you are here because of that announcement that went through their department as well. And also thank Professor Satish Nagarajaya from Rice University for being here and also participating quite actively in this program.
By lending his jacket.
Also want to thank Professor S. Gopalakrishnan, convener of our center, for wholeheartedly supporting and then encouraging programs like this to come up, which would benefit all the students and the researchers here. Our thanks are also due to Axis Bank for the generous CSR donation, which helps us in actually doing these kinds of activities all through the year. And also to Department of Physics for lending us this auditorium. Some of you would have observed that our lecture was supposed to be in the aerospace department, but we had to shift in the last minute because of some, say, one more program coming up there. So in the last minute, Department of Physics allowed us to use their auditorium, so special thanks to them. And also special thanks to my colleague Vivek for organizing this so nicely and also taking care of all the required things. And definitely, not the least, the participants for being wonderful audience and also coming up with some excellent questions, which even the speaker appreciated it. So very nice, and thanks for making this program such a successful one. Now I request all of you to join us for the lunch, which we have arranged in the ground floor. The lunch is ready, so I think we can all walk towards it. You can take the stairs which is behind this auditorium. So once again, thanks to everyone for making this program a grand success.